Algorithms design and analysis, divide and conquer, binary search, merge sort, quicksort, and Strassen's matrix multiplication. Welcome to this lecture on algorithms design and analysis. In this session, we are going to study one of the most important algorithm design paradigms in computer science, known as divide and conquer. Using this strategy, we will explore several famous algorithms, including binary search, merge sort, quicksort, and Strassen's matrix multiplication. These algorithms are extremely important because they demonstrate how a complex problem can be transformed into smaller and simpler problems, making computation more efficient and elegant. Let us begin with the divide and conquer strategy. The phrase divide and conquer literally means breaking a large problem into smaller pieces, solving those pieces independently, and then combining the results to obtain the final solution. This is one of the most powerful design techniques in computer science. The basic idea is surprisingly simple. Suppose we have a large problem that is difficult to solve directly. Instead of trying to solve it all at once, we divide it into smaller subproblems. Each subproblem resembles the original problem, but has a smaller size. Once the problem is divided, we solve each of these smaller subproblems. If a subproblem is still large, we apply the same strategy again, dividing it further into even smaller subproblems. This recursive process continues until we reach a stage where the problem becomes very small and can be solved directly. Finally, after obtaining solutions to all the smaller subproblems, we combine these partial solutions to produce the solution to the original problem. Therefore, divide and conquer consists of three major phases. The first phase is divide. In this phase, the original problem of size n is partitioned into smaller subproblems. Usually, these subproblems are of equal size, such as n by 2 or n by k. The second phase is conquer. Here, each subproblem is solved recursively. If the subproblem is small enough, we solve it directly without further recursion. This direct solution is known as the base case. The third phase is combine. In this stage, the individual solutions obtained from the subproblems are merged together to form the final solution of the original problem. Many famous algorithms are based on this simple yet powerful idea. To analyze divide and conquer algorithms mathematically, we use a recurrence relation. A general recurrence can be written as follows. The running time t of n is equal to multiplied by t of n divided by b plus f of n. In this equation, the parameter a represents the number of subproblems generated during division. The parameter b represents the factor by which the problem size decreases. The function f of n represents the work required to divide the problem and combine the solutions. If the problem becomes very small, a direct solution is applied, and the running time is represented by another function, usually denoted by g of n. Solving such recurrence relations manually can become difficult. Therefore, computer scientists use a powerful mathematical tool called the Master Theorem. The Master Theorem provides a direct method to solve recurrence relations of the form t of n equals a multiplied by t of n divided by b plus f of n. There are three important cases. In the first case, if the function f of n grows slower than n raised to the power log base b of a, then the recursive calls dominate the running time. In this situation, the solution becomes theta of n raised to the power log base b of a. In the second case, if f of n grows at exactly the same rate as n raised to the power log base b of a, then the work is distributed equally across all levels of recursion. The solution then becomes theta of n raised to the power log base b of a multiplied by log n. In the third case, if f of n grows faster than n raised to the power log base b of a, then the work done outside the recursive calls dominates the running time. The solution in this case becomes theta of f of n. The Master Theorem is extremely useful. because it allows us to determine the time complexity of many divide and conquer algorithms in just a few steps. Now, let us move to our first divide and conquer algorithm, binary search. Binary search is one of the fastest searching techniques available for ordered data. However, there is one important condition. The array must be sorted. If the elements are not arranged in sorted order, binary search cannot guarantee correct results. The main idea behind binary search is very intuitive. Instead of checking every element one by one, we repeatedly divide the search space into two halves. Imagine you are searching for a word in a dictionary. You do not start from the first page and move sequentially. Instead, you open the dictionary somewhere in the middle. If the word you are searching for comes alphabetically before the current page, you ignore the second half. If it comes after the current page, you ignore the first half. You continue this process until the word is found. Binary search works exactly in the same manner. Initially, we maintain two variables called low and high. Low points to the beginning of the array. High points to the end of the array. Next, we compute the middle position. If the target element is equal to the middle element, the search ends successfully. If the target is smaller, we discard the right half of the array. If the target is larger, we discard the left half. This process continues until either the element is found or the search interval becomes empty. Let us consider an example. Suppose we have a sorted array containing the numbers 10, 14, 19, 26, 31, 35, 42, and 44. We want to search for the number 35. Initially, low is 1 and high is 8. The middle position becomes 4. The element at position 4 is 26. Since 35 is greater than 26, we discard the left half and continue searching in the right half. Now, low becomes 5 and high remains 8. The middle position becomes 6. The element at position 6 is 35. Since the target matches the middle element, the search stops successfully. Thus, binary search finds the element after only 2 comparisons. This demonstrates the power of divide and conquer. The time complexity of binary search is very efficient. At each step, the search space becomes half of its previous size. Therefore, the recurrence relation becomes T of n equals T of n by 2 plus a constant amount of work. Using the Master Theorem, we obtain the solution theta of log n. This means the running time grows logarithmically with the input size. The best case occurs when the target is found immediately at the middle position. In this case, the running time is theta of 1. The worst case and average case are both theta of log n. The iterative version of binary search uses only a few variables and therefore requires constant space. However, the recursive version requires theta of log n stack space because of recursive calls. Next, let us study merge sort. Merge sort is one of the most elegant sorting algorithms based on divide and conquer. Its working can be understood in 2 phases. The first phase is division. The second phase is merging. Suppose we have an unsorted array. Merge sort divides this array into 2 equal halves. Each half is then divided again into smaller halves. This process continues recursively until every subarray contains only one element. Since a single element is already sorted, the algorithm then starts merging. During the merge phase, 2 sorted subarrays are combined to form a larger sorted subarray. This process continues upward until the entire array becomes sorted. Let us take an example. Suppose the array contains the elements 38, 27, 43, 3, 9, 82, and 10. The algorithm first divides the array into 2 halves. The left half contains 38, 27, and 43. The right half contains 3, 9, 82, and 10. Each half is divided again. Eventually, we obtain arrays containing only one element. Now, the merge process begins. 38 and 27 are merged to produce 27 and 38. Next, this result is merged with 43. Similarly, 3 and 9 are merged. 82 and 10 are merged. The resulting sorted arrays are combined step by step. Finally, the complete sorted array becomes 3, 9, 10, 27, 38, 43, and 82. The beauty of merge sort lies in its consistency. Its performance does not depend on the initial arrangement of elements. Whether the input is sorted, reverse sorted, or random, the running time remains the same. The recurrence relation for merge sort is T of n equals 2 multiplied by T of n by 2 plus n. The two recursive calls represent the sorting of the left and right halves. The linear term n represents the merging process. Applying the Master Theorem, we obtain the result theta of n log n. This means that the best case, average case, and worst case all have the same complexity, namely theta of n log n. However, merge sort has one disadvantage. It requires additional memory for the temporary array used during merging. Therefore, its space complexity is O of n. Now, let us move to another famous sorting algorithm, quicksort. Quicksort is one of the fastest sorting algorithms used in practice. Unlike merge sort, quicksort does not divide the array exactly at the middle. Instead, it chooses an element called the pivot. The pivot acts as a reference point for partitioning. During partitioning, all elements smaller than or equal to the pivot are moved to its left. All elements larger than the pivot are moved to its right. After partitioning, the pivot automatically reaches its correct position in the sorted array. The algorithm then recursively sorts the left and right partitions. An important advantage of quicksort is that it does not require a merge step. Once partitioning is completed, the subarrays are already positioned correctly relative to each other. Let us consider an example. Suppose we have the array 24, 9, 29, 14, 19, 27, and 11. We choose 24 as the pivot. We use 2 pointers. One pointer moves from the left side. The other pointer moves from the right side. The left pointer stops when it finds an element greater than or equal to the pivot. The right pointer stops when it finds an element smaller than or equal to the pivot. If the left pointer is still before the right pointer, we swap the two elements. This process continues until the pointers cross each other. Finally, we place the pivot in its correct position. After partitioning, the array becomes 19, 9, 11, 14, 24, 27, and 29. The pivot 24 is now in its final sorted position. The algorithm then sorts the left and right parts recursively. The performance of quicksort depends heavily on the choice of pivot. In the best case, the pivot divides the array into 2 equal halves. The recurrence becomes 2 multiplied by T of n by 2 plus n. The time complexity is theta of n log n. In the worst case, the pivot becomes either the smallest or the largest element. This happens when the array is already sorted or reverse sorted. The recurrence becomes T of n equals T of n minus 1 plus n. The solution becomes theta of n squared. Fortunately, the average case performance of quicksort is theta of n log n, which makes it extremely efficient in practical applications. The space complexity in the average case is O of log n, due to recursive calls. Finally, let us discuss Strassens matrix multiplication. Matrix multiplication is a fundamental operation in computer science, used in graphics, machine learning, scientific computing, and artificial intelligence. The conventional matrix multiplication algorithm uses 3 nested loops. If 2 matrices are of size n by n, the total number of multiplications becomes n cubed. Therefore, the time complexity is theta of n cubed. For many years, this was considered unavoidable. However, in 1969, the mathematician Volker Strassen introduced a remarkable improvement. Strassen observed that matrices can be divided into 4 equal submatrices, instead of performing 8 recursive multiplications as in the standard divide and conquer approach. He found a clever way to perform only 7 multiplications. Although this method requires additional additions and subtractions, Reducing one multiplication at every level of recursion produces a significant improvement in the overall running time. The recurrence relation for Strassen's algorithm becomes T of n equals 7 multiplied by T of n by 2 plus n squared. Applying the Master Theorem gives the solution theta of n raised to the power log base 2 of 7. This value is approximately theta of n raised to the power 2.81. Therefore, Strassen's algorithm reduces the complexity from O of n cubed to approximately O of n raised to the power 2.81. This was a groundbreaking result because it proved that matrix multiplication could be performed faster than cubic time. However, Strassen's algorithm also has some limitations. It requires additional memory for temporary matrices. It performs many additions and subtractions, which increase the constant factors. For small matrices, the conventional method is often faster. Furthermore, Strassen's algorithm can introduce numerical errors because of subtraction operations. Despite these limitations, Strassen's work opened the door to a new era of research on fast matrix multiplication algorithms. To summarize this lecture, we studied the divide and conquer paradigm, which solves problems by dividing them into smaller subproblems, solving them recursively, and combining their solutions. We then explored binary search, an efficient logarithmic time-searching algorithm. Next, we studied merge sort, a stable sorting algorithm with guaranteed n log n performance. After that, we discussed quicksort, one of the fastest practical sorting algorithms based on partitioning around a pivot. Finally, we examined Strassen's matrix multiplication, which improved the complexity of matrix multiplication from cubic time to approximately n raised to the power 2.81. These algorithms are not only important for examinations, but also form the backbone of modern computing systems and advanced algorithmic research. Thank you for listening, and in the next lecture, we will continue our journey into more advanced topics in algorithms design and analysis.